Okay, let's go ahead and get started. Anybody bring any questions from last time on relations and functions? Okay. The video on that is already up, so if you need it, it's up. Does everybody know where the videos are? You might have trouble finding them. They're in the last section under logic, because that's where the final exam is also. So I'm putting these in order as we do them in that section under content. Okay? All right, so today what I want to do is go over graphs, and what that leaves us then is next week we'll do combinatorics and proofs, those two quizzes. And then the week following that, which is the week before Thanksgiving, I believe, hope so, is the final exam. Okay? And that'll be online, and it'll come up on Monday and then continue through till the following Sunday. Okay? So that gives you a chance to take it once before class period and to ask questions in class. All right? Okay. So let's start with graphs. Okay, so this is on terminology. So the edges of that graph are V1, V2, V3, V4, or V5. Is that correct? Are those the edges?
Yes.
No, those are the vertices. Okay. And here's the clue. V stands for vertices. So, I mean, I don't mean to be demeaning, but these are vertices. What are the edges? The edges are the lines. Think of the edge of anything. It's a line, isn't it? So the edges would be V1 comma V3, or V3 comma V2, or V2 comma V3. This is a non-directed graph, isn't it? There are no arrows, right? So the edges are the lines. The vertices are the points. When you draw a, everybody know what a UML is? Graph? Okay. When you draw a graph like that, what do you have? You have boxes that show activities, right? Which are probably snippets of code, or they are going to database graph files. The lines, though, between them are what connects those two, the order in which you go through that graph. Those are the edges. And what those lines are showing is there's a relationship between this activity and the next activity, or this activity and the file that it needs to go access. Those are very important concepts, and they relate right back to what we've been talking about in relations and graphs. Okay? So those are all graphs. So this answer is false. These are not the edges, these are the vertices. Okay. In this drawing here, V1, V3, V4, V5 is a walk from V1 to V5. Well, let's see. V1, V3, V4, V5. Is that a walk? Why is it not a walk?
Because the V3 and V4 are connected.
Yeah, V3 to V4 does not have an edge, does it? They're not connected. So therefore, that is not a walk from V1 to V5. Okay. Okay, true or false? There are two paths from V4 to V1. Are there two paths from V4 to V1?
Yes.
There are, aren't there? We can go V4, V5, V1. Since this is a non-directed graph, I can go V4, V2, V3, V1. Those are two different paths. Okay. Okay, yeah, there are two walks from V4 to V1. Is that true? Are there two walks from V4 to V1? No? What's the answer?
There are. Yes.
Hmm? The answer is?
Yes.
The answer is there's infinitely many walks.
Oh, it's true.
And the reason is the difference between this one and the last one. For a path, there is a uniqueness, isn't there? You cannot cross an edge more than once. With a walk, you can repeat edges. So for instance, I can go V4, V5, V1, or I can go V4, V5, V4, V5, V4, V5, V1, can I? And then I can go V1, or wait, V4, V2, V3, V1, that's another one. Or I can go V4, V2, V3, V2, V3, V2, V3, V1. I can go back and forth along an edge as many times as I may want to. Makes no sense. However, if you were to do a UML drawing, you may have a situation where you go to another activity and you check for errors, and if there's an error, you go back, right? And you may go back and forth several times trying to find a hit. For instance, if you were looking at a file sequentially, looking for a particular entity, and you didn't find it, you may go back and read it again, right? For the next record. So there's an example of a walk that can happen multiple times. Right, does that make sense? So remember, walks can repeat, paths cannot. Okay. Does this graph have a Euler circuit? Well, Euler circuit says I can start at a vertex and I can make it all the way around the graph and back to that same vertex without crossing an edge twice. So if I start at V5, go V1, V3, V2, V4, back to V5, that's a Euler circuit, isn't it? Okay. So the answer is true. Is G connected? Well, let's look at what a disconnected graph could look like. If I had V1, V3, V2, V4, and V5. Now I've got about the same pattern of vertices, don't I? But look at this. I could put an edge here, an edge here, an edge here, and an edge here. That is not a connected graph. The reason it's not connected is this section down here has no connection with this section up here, does it? So by taking out the V2 to V4, that edge, I've now formed a disconnected graph. So when you look at a graph, if there's no path that can get you from one point to the end, okay, then it's disconnected. There's something missing there. Okay. Okay. Now, what do we call this graph that's different from the rest of them we've seen?
It's directed.
This is directed, isn't it? Because it has arrows. Meaning that this edge V1 to V3 is an edge, but V3 to V1 doesn't exist. Okay? So looking down here, it says the edges of G are V1, V3. Well, that's the one we just looked at. V3, V2, V4, V2, V4, V5, and V5, V1. So the answer is yes, those are the edges, aren't they? Okay. Now, if it had listed any of those where you would have to go backwards across the arrow, that would not have been valid. This was valid only because it did follow the arrows. Is that clear? Okay. Okay. A directed graph, in a directed graph, if there's a path from vertex V to vertex V1, then there's a path from V1 to V. Is that true or false? It's a directed graph, right? And so just like in that last one, this is V prime, and this is V, and I've got an edge from V prime to V. Do I have a graph from V to V prime? Or to look at it in the way they said it? So I do have a path from V to V prime. Do I have a graph? Do I have an edge from V prime to V? No, I don't, do I? Because in a directed graph, you only mention it in the direction it's going. Now, it could have been if this was V2, let's call it, and then this was V prime. That would have been still okay, because I'd still have a path from V to V prime, don't I? Following the arrows. But I do not have a path from V prime to V. Okay? Now this was something that was confusing for some, so let's go through it. And that's the adjacency matrix. Adjacency means next to. And adjacency is defined as connected by an edge. So when we look at an adjacency matrix, we want to mention all the vertices. V1, V2, V3, V4, and V5, and then go down the edge, V1, V2, V3, V4, and V5. Now, you start here and you say, is V1 connected to itself? Is it adjacent to itself? Well, there is no edge from V1 to itself, is there? What would that look like? Well, this could be an edge. It's called a self-loop. Okay? But there are no self-loops on this one. So therefore, V1 is not connected to itself, and we put a 0 there, meaning no. Is V1 connected to V2? Adjacent to? No. There's no edge connecting V1 and V2. So we would say 0 there. How about V3? Is V1 connected to adjacent to V3? It is, isn't it? We have an edge going from V1 to V3. Therefore, it's adjacent. We put a 1. How about V4? Well, no, there's no edge from V1 to V4, so therefore that's a 0. but there is an edge between V1 and V5, so that's a 1. How about V2? Well, we could go to V2 and we can say, well, wait a minute, V2 is adjacent to V3 and V4, because that's where the edges go. So we could just shortcut this and say V3 and V4 and not for the others. As we go to V3, we notice V3 is adjacent to V2 and it's adjacent to V1. So V3 is adjacent to V1 and V2, but not the others. V4 is adjacent to V2 and V5. V2 and V5, but not the others. And V5 is adjacent to V1 and V4, but not the others. Okay, so if I see how that works, okay, it's where the edges are. And it's one edge, a single edge has to be between the two. Okay. Now that's an adjacency matrix, but this is a non-directed graph, isn't it? So I could say that V4 and V5 are adjacent, and V5 and V4 are adjacent, and V4 and V5 are adjacent, because it's non-directed. Now the next question just asks about the same graph, except that we're now looking at it in a directed sense. So now it says, what's the adjacency matrix for this one? Well, it's going to be less than the other one, because it's going to be dependent on the direction. So if I look at V1, V1 is adjacent to V3, isn't it? It's not adjacent to V5 anymore, because the arrow's going this way, not that way. So the only thing for V1 is V3. So we take off this one and make it a 0. So a directed graph is going to have fewer adjacencies. V2 is not adjacent to anything, is it? Because everything is adjacent to it that is adjacent, but it's not adjacent to it. So V2 now, take out these ones and replace them with zeros. V3 is adjacent to V2, but that's all, because this arrow is coming in. So for V4 is still adjacent to V5, and it's adjacent to V2, because the arrows are coming out of V4. So this is still okay for V4. V5, though, is only adjacent to V1, not to V4. So there is a relationship between the two adjacency matrices, okay? Does that make sense? Does everybody see the difference? Okay. That takes care of the graph quiz. Does anybody have any questions on graphs? Everybody okay on it? Okay. Do you remember the puzzle about the bridges? Conan'sburg, whatever it was? And why that didn't work? What was the trick to solving a problem like that? Yes?
It's only possible if you have exactly 2 odd vertices.
Or none.
Or none.
Yeah, it does work for none. But if you're going to have any odd vertices, you must have only 2. If you have none, it turns out you can start anywhere. Okay. So that's graph terminology. Okay, what I want to do is hold off then on combinatorics and the proofs, because we can do both of those next week fairly easily. And this kind of brings us up to where we need to be for this week. Okay. So we've done relations, functions, and graphs this week. And this one will be up, I hope, by this evening. Okay. So any questions? Has everybody got their project in? Hope so. Okay. Everybody done? Anybody have any questions on the project now that it's in? Except what your grade is, right? Okay. I'm pretty lenient on grades, yes.
Whenever I did the 10,000 iterations, it would just crash. Is that because my computer sucks?
You probably burned it up. I don't know. I don't know. Because all you did was it just an answer to your prompt up above? You didn't change the code any?
Like, it would say, I made it so I would ask you how many times you want to iterate it.
Yeah.
And you do 10,000, and it would go, and then it would just error out and crash.
Did you interpret what error it was?
It was like 50 different errors, and it would just crash before I could read all of them.
Really? That's interesting. Yeah, I don't know. Yes.
I have an idea as to what it might be. By chance, were you saving each of the different 10,000 arrays to a different array, or were you overwriting the same one over and over?
It was just overwriting the same one.
Okay. Because it could have been a memory error if it was 10,000 arrays all at the same time, but if it was the same one, that shouldn't happen.
Interesting. Yeah, that could have, I could see where that would overflow memory eventually. Yeah, yeah. Okay. Anybody have any unique findings that they got from their project that they want to share? How many got the selection sort slower than the bubble sort? Anybody have bubble sort being the best? So do you have an idea why it might have been the best?
Maybe, not really sure. I wasn't really thinking about it.
Okay. I've had that happen before, yes. Did you have the same thing?
Well, I was just saying that I think the reason that the bubble sort was slower is because it kept calling the swap method more times.
Mm-hmm. Yeah, that was the answer to the literature, okay? But as I said in class, I'm not going to mark somebody wrong if they got the other responses, okay? Because there are interesting things, I've seen it happen before, where for some people the bubble sort performed better. We never did quite figure out why. But yes, by the literature and by the coding itself, selection sort does not swap except once per cycle, right? It reads all the way through and decides what's the lowest or highest, depending on which way you're going, value, and it puts it in the next slot. The bubble sort is constantly swapping all the way along, well, as it sees a need to. Yes?
I also noticed that sometimes bubble work would make itself do more work, as in it would move a number farther away from its index, just trying to move another number to the end. Like with selection, once it found the minimum, it would put it in the right spot, and then it was done with it, it wouldn't question it.
Yeah, correct.
It kind of almost did too much work.
The bubble sort did too much work. Yeah, it does. Yeah, but you know what the interesting thing is, the bubble sort's easier to understand. If you're trying to understand the two of them, the bubble does make more sense to the understanding of it. And so that's the one that was used for a long time. I used bubble sort quite a bit when I was writing on the original PC. It was not a Windows machine. It had very little available to it except for a very archaic version of BASIC. It didn't even have index file support. So on that machine, I had to create my own index file technology, and I had to sort the index. And so I used a bubble. Okay. But it was for small businesses with less than 100 customers, because I couldn't go over 100 without blowing memory. Okay? Yeah, there are all kinds of things. Yes?
So Since they're both algorithms with like nested loops in them,
Uh-huh.
does it make a difference whether bubble sort does everything in the second nested loop and then selection sort does it in the first?
Absolutely, that's a good way of looking at it, yes, because the second one runs n squared times, the first one only runs n times, doesn't it, at most? Okay. So absolutely, yeah.
I don't know if I would be nitpicky.
That's another, I know that's, I haven't had anybody say that, but it's obviously logical, yes, excellent. Yeah. Okay, yes,
Also, I was just thinking that you probably get those to run faster if you use the while loops outside, whether or not it checks if the swap method was called at all, to know whether or not it's done, because both of those particular examples that was on the paper,
mhm.
those went through the entire thing, all the iterations, no matter what.
Ah, good point. So while would not, because it was,
Yeah,
got a
because if it-
conditional setup.
Yeah, I would see whether or not it's actually done sorting it.
Yeah.
Instead of the ones that we got from the example,
Mhm.
just to go through it completely.
Right, right. Well, doesn't the bubble sort stop after it has no swaps?
Not the one that was provided.
Really?
That you specifically told us to use.
Okay. That's, well, see, I looked at it, right? Yeah, the one I knew checked at the end of the inner loop. If it had had no swaps, it dropped out, no matter where it was. Okay, anything, somebody else says something? Okay. Well, it sounds like you all did some thinking, which is really what I wanted to see. And I'll be looking at them within the next week or two, kind of get through them. I have 4 sections, by the way, so if you wonder why it takes a while to get things done in this class, it's because I've got, well, 40 times 4, that's 160 students, right? Okay. 160 students in this particular subject, okay, as well as another topic. All right, so that really does it for today.